All right, welcome back. So here's the deal. We've been really focusing on what is known as one variable hypothesis testing. Today we're going to get into two variable hypothesis testing. The main difference really is just how many groups of people you're talking to. So in one variable, if you notice, we've been testing, for instance, means and percentages, but we always gather just one group of people to test that. In today's lesson and in subsequent lessons, we are going to be doing more than one group. And for this class, we're only going to stick to two groups of people. Anyway, the beginnings of this is this concept of independent and dependent samples. So we're going to learn how to test the differences between two means when it's a large sample, meaning the sample size is 30 or more, and when the samples are what are known as independent. So here's what I mean by that. Let's start with that part first. So independent versus dependent samples. Here are two examples, and one of these is independent, the other is dependent. So take a look at example one. Sample one, resting heart rates of 35 individuals before drinking coffee. And then sample two, you're going to collect information from their heart rates after drinking 2 cups of coffee. Now, in sample 1 and 2, you're measuring 2 times, so therefore there's your two groups, two variables. But you're going to notice that there are literally the same people in both sample 1 and sample 2, same 35 individuals, except you're measuring 2 different things. One before they drink their coffee, their heart rate, that is, and then once after drinking 2 cups of coffee. And any predictions? Yeah, chances are the heart rate's going to increase. This is what is known as a dependent sample. So the second sample depends on that first sample. Without that first one, there's really nothing to compare it to. So that would be known as a dependent sample. This is not what we are learning how to do today. What we are learning how to do is comparing two different groups or two different samples or two independent samples. This is example 2, for instance. Sample 1 is the test scores of 35 statistics students. Sample 2 is the test scores for 42 biology students who do not study statistics. These are two complete separate groups, and I don't know exactly what this statistics is focusing on, but one is going to be the test scores for stat students, and then sample 2 is going to be the test scores for biology students. And now this could be, for instance, maybe like there is I don't know, some kind of math test that they're taking, and they're trying to see who does better, either people with statistics backgrounds or people without statistics background. Maybe that's what this is all about. But this is known as independent because of the fact that these two groups have nothing to do with each other. They're completely independent of each other. Now we are going to be focusing on problems like example 2, where again, two variables or two groups of people, but completely separated from each other. So let's get into an example and see how one is done. Here's the problem. A consumer education organization claims that there is a difference in the mean credit card debt of males and females in the United States. Results of a random survey of 200 individuals are shown below in this table. Do the results support this organization's claim? So what they're claiming is that there is a difference between credit card debt of men and credit card debt of women. And that is pretty much the claim. So let me show you how the null and the alternative works for these problems. It's going to be slightly different than before, but not altogether too different. And you're going to notice that with these problems, they're going to give you two sets of data. They're just going to give you a mean, a standard deviation, and a sample size for group 1. And then they're going to give you a mean, a standard deviation, and a sample size for group 2. You're always going to have these two groups, hence two variable problem. Now, for the null and the alternative, let me write this down for you. The claim is that the first group is going to be different than the second group. Think of the different 6 symbols we've used when writing null and alternative hypotheses, like equal signs, not equals, less than, equal to, greater than, so on and so forth, or so on and so forth. Which one do you suppose is going to be this one if it's different? And if you thought not equal to, you're absolutely correct. But the question is, what is not equal to what? What do we write here? And this is what we're going to write. It's going to look something like this. The mean 1 is not equal to mean 2. That's our alternative hypothesis, and that's our claim. And the reason why our claim is the alternative is because, again, not equal to, that's where we are alternative, same as before. But you notice that instead of having a mean being compared to a number, we are comparing two different means now. So the mean of the first group and the mean of the second group, mean of the women, mean of the men. And the opposite of that would be that they're equal to each other. And we're just trying to test to see if this claim is true, if that they're indeed different from each other. So that is step number 1. Step 2 is still doing the tails test. And good news is the tail test is going to work identical to the way we've done it before. We're going to need a z-score for the 0.05. And because this is a not equal to, we're going to be doing a two-tail test. So just like before, you're going to go to your t-table. You're going to go to a two-tails chart. You're going to go to 0.05. And then you're going to go find that z-score 1.96 and put it on both the left and the right side of this tail test. So the next step isn't going to be completely a shocker to you. It's going to look something like this. Now, the part that is going to be different is going to be the math part, as you probably guessed it. And this is what the math equation that we're going to be using for these problems looks like. Now, if you look in the statistics textbooks, they're going to look a little different than this. I've tried to simplify this a little bit. So just a heads up, when you get to a college level stats class, they might look, they're going to do similar problems to this, but they just might look a little different, but entirely pretty much the same thing. So on top of this, on the numerator, you're going to have the two means subtracted from each other, always group 1 minus group 2. So it's going to be important that whatever group 1 is, you want to keep it consistent and group 2 consistent. You're going to have that divided by the square root part. Now, the square root part is known as the standard deviation of the difference of means. This is the part that I've kind of abridged and just kind of put all the stuff together for you. Usually people will calculate this by itself. So what this is the standard deviation of the first group squared divided by the sample size of the first group plus standard deviation of the second group squared divided by the sample size of the second group. Hence, you get the 1s and the 2s. So that's to denote the first group and then the second group. So usually what people will do is they'll calculate this bottom part first and then subtract the two means, divide by whatever the answer to this bottom part is, and there is your test statistic. And that will be eventually how we test to see if this claim is true or not. So let's put this number, all the numbers from the problem into this. It's going to look something like this. So the mean, again, of the first group, subtract from the mean of the second group. And then you have all the standard deviations and the sample sizes all placed in where they belong. So give you a second to try to calculate this. This is the part where people usually make mistakes because they're doing an order of operations wrong. So I'm going to have you pause this video, try to calculate it, and make sure you're getting the same thing I am. All right. So hopefully you paused it, but here's what I'm getting. I'm getting 77.54 when you square root the bottom piece. And when you do 2,290 minus 2,370 divided by that, you end up getting negative 1.03. Now, if you're just a little bit off because you rounded funky and you're just off, like give or take a little bit, it's totally fine as long as you get the main gist of this. That should be good. Okay. So just as before, negative 1.03, think of this as a number line. Negative 1.03 would be between these two barriers. So that means we are in the unshaded section. That means HO is true, HA is false. And because our claim is in the alternative, that would mean our claim is false. So we do not have enough evidence to support this organization's claim because this claim is false. Probably the alternative true is that it's the same, that the mean credit card debt is the same for males and females is probably what we can conclude. But that is how you would do one of these problems. Let's do a separate problem real quick. This one we'll do a little bit quicker. So here we go. Survey indicates that the mean per capita credit card charge for residents of New Hampshire and New York is $3,900 and $3,500 per year, respectively. The survey includes a randomly selected sample of 50 from each state, sample standard deviation of $900 from New Hampshire, $500 from New York, and a level significance of 0.01. Is there enough evidence to conclude that the mean per capita credit card, blah, yada, yada, yada? The first thing that you'll notice I'm doing is I'm breaking down the means into groups, right? So in New Hampshire, I have dictated as group 1, and New York, I've dictated as group 2. So I put all that information from the text in there. Now, you'll notice for both of these last two few problems that the sample sizes are always identical for group 1 and group 2. It doesn't always have to be the case as long as they're more than 30. That would be a large sample. Now, the thing that does matter is they have to be 2 independent samples, and obviously people from New Hampshire are independent of people from New York. So these are 2 separate groups of people, which is why this is, again, an independent 2-variable test. So I got that part all settled. Now let's take a look at what happens next. Because we are testing that New Hampshire is more than New York, we are going to have the first mean going to be greater than the second mean. The greater than would make the alternative be mean 1 is greater than mean 2 because there's no equal sign. The null would be less than or equal to because that is opposite. This would be a one-tail test. So if you look on your z-score, a one-tail test at that level of significance would be 2.326. Then going to go ahead and plug in my numbers into my test statistic equation, and you can go ahead and pause if you'd like. Go ahead and see if you calculate that correctly. Here's what I got. So when I did all the square rooting and everything, and then went ahead and square rooted it, when I divided at the very, very end, I end up getting 2.75. Now, 2.75 is going to be in the rejection zone because that is greater than 2.32. So that's going to be in the shade area. That means HO is false, HA is true, which means, yes, indeed, that this claim is true, that the credit card charge is higher in New Hampshire than it is in New York. So that would be the answer to this problem. So if you have any other additional questions, feel free to stop by office hours. If not, you guys have a wonderful day. The assignment today should hopefully be pretty straightforward. It's going to be very similar to these problems. And same with the attendance task. You guys have a wonderful day. All right, bye.